And next up, we have Michael Anderson of the Aerospace Corporation presenting a live demonstration of SDR with AI and cloud services. Michael, it's all yours.
Thanks, Brandon. And let me go ahead and share the screen here. There we go. So I'm here to talk about a project that we have called Samosa. It is an SDR with AI and multi-mission open systems architecture. We have a number of contributors working on this project. You see them listed there. Certainly, we could not be anywhere that we are right now without the help of all these folks coming together and contributing their respective levels of expertise. So let me get into this real quickly here. What Samosa is all about is we thought that as we were going through kind of seeing what new missions would be coming up and what things that customers were interested in, that is the folks that we're working with, we knew that we were going to have more and more requirements for software-defined radios, for accessing AI, for being able to combine AI and RF together. We were focusing on trying to develop a kind of foundational CubeSat network, a framework for being able to extend a networked payload architecture, and focus on multi-mission proliferated constellations. In particular, trying to keep with the MOSA, the open systems architecture approach, being able to then use the AI to reconfigure the mission of the radio over, let's say, certain areas of the world. So we're doing SIGINT in some places, and we're doing search and rescue in others. The idea is bringing together this nexus of artificial intelligence, software-defined radio, and cloud computing, and then tying that together with a spacecraft bus interface and being treated as a payload. So as we're bringing these elements together, we're looking at some relevant mission areas, trying to understand where an AI engine and software-defined radio integration actually makes sense. How do we go about leveraging that AI coprocessor and, of course, the AI framework, whether that's TensorFlow or PyTorch or what have you? And then demonstrating the integration of that machine learning with the software-defined radio. In the software-defined radio element, we're focusing on trying to take existing commercial off-the-shelf components, and in this particular case, we're actually using a 5G radio, something that was built for 5G cellular systems, originally funded by DARPA, and employ it in a more space-oriented mission, something that's not going to be focused on terrestrial applications, but spaceborne applications. Using the modularity of the digital signal processing, of the modularity associated with FPGAs and programmable logic, all in one package that ties together the AI and the SDR portion. Now, in order for us to be able to make it a true multi-mission application, we also need to be able to task this thing with the potential of even doing partial reconfiguration of the FPGA for certain mission sets. So we looked at where that might make the most sense, and that was taking a look at a page in the cloud world these days, where folks are interested in systems like Kubernetes and the deployment of software inside of containers. So prototyping some mission-specific basic, cloud-based capabilities, and focusing on understanding what the impact of the enterprise mission interface. I mean, obviously in the case of aerospace, we're focused on the space enterprise. So how do we take those enterprise concepts from the ground and from the ground stations and move them on orbit? With an emphasis of trying to do as much computation on orbit as possible. Obviously, the more things we have to downlink to the ground, the longer that takes, the greater the latency being employed, and therefore potential missing of particular mission opportunities. So different use cases that we've identified so far, of course, ISR, intelligence, surveillance, reconnaissance, being able to collect and identify waveforms and then identify those waveforms via machine learning architectures. We will show a demonstration of doing that. We also have been approached by some customers to consider, PNT applications where we're looking at position, navigation, and timing. We've actually looked into the potential for the new generation of this platform we've been working on to incorporate a chip scale atomic clock in order to get us the kind of performance that we need to have in order to be an alternative PNT source. Of course, protected waveform, location interferometry, where we have potential for multiple channels and phased array antennas to be able to do beam forming and do geolocation. Of course, SIGINT, anytime you have a fairly wide bandwidth radio, which we do in this case, we'll talk more about that here in a moment, but support the idea of doing broad spectrum sampling, channelization, and it turns out that this particular part has also been successfully employed in synthetic aperture radar and military radar applications, as well as civilian radar applications. So there are there's quite a bit of flexibility in the platform, and it really is just focused on trying to nail it down to specific missions for some demonstration purposes. And the very first one that we've kind of keyed on and we'll show in the demonstration is this idea of being able to collect and identify waveforms using machine learning architectures. So the general approach for Samosa is we are a payload. We are not the flight software that's controlling the actual spacecraft. We're a payload, a hosted payload on this platform. We interface to the spacecraft bus for things like ephemeris, but for the most part, we are a separate payload that does not interface with the operation of the spacecraft at all. Just from a perspective of, because of the things we're doing here, we're trying to leverage Linux and Kubernetes and a few things that have obviously not had a whole lot. I mean, Linux has got some good experience in space, but things like Kubernetes and Docker don't have a lot of heritage in space at this point. So we wanted to make sure that as a hosted payload, we didn't interfere with the spacecraft, but we could then interface with the spacecraft bus, and pull information off the spacecraft as necessary for whatever mission it is that we were being tasked for. The basic device that we're using for this particular radio is the Xilinx RF SOC. Now, the RF SOC is a device that has basically got a quad-core ARM Cortex-A53. It's got the full neon floating point unit. It has a fair amount of computation in and of itself. Of course, we have memory. There is a real-time processing unit out there. We haven't taken advantage of the real-time processor as of yet, but that's another element that we're looking to factor in here in this FY. We are also looking at some of the security elements here, of course, with Trust Zone. How do we guarantee that we have an authenticated boot cycle, establishing a core root of trust and guaranteeing that the platform has not been compromised in some way? Of course, there's quite a bit of connectivity. We have gigabit Ethernet, we have CAN, we have SPI bus, and through some of the programmable logic, we can also get to SpaceWire and other spacecraft-specific buses. In the programmable logic, we do have anywhere from 8 to 16 different radios. We have both high-speed RF ADCs and DACs. The ADCs right now for our particular generation of the part are running at up to 5 gigasamples per second. That jumps up to 7.125 gigasamples per second in the next generation. Our DACs are capable of 5 gigasamples per second in terms of being able to go digital to analog. We do have some high-speed I/O out there, and we've also incorporated an interface to the open source, aerospace-sponsored open source platform, which we can either use it for Ethernet or we can use it for general purpose I/O. So we'll get into some of the details on that here in just a moment. Key architecture components here is the use of the RF sock. Again, this was a terrestrial part focused largely on 5G radio applications. Then taking that and using the capabilities of that particular part, it does have access to either 8 or 16 channels. And in case, when we're talking about bandwidth here, for the 8-channel first generation parts, we're talking 200 megahertz of instantaneous bandwidth across of each one of the 8 channels. That jumps up to double that, basically. We go to 400 megahertz of instantaneous bandwidth across 8 channels in the 3rd generation parts. And that's in frequency range 1, that is below 7.125 gigahertz. Above that, in frequency range 2, from the cellular world's perspective, which is in the millimeter wave range, we jump up to about 1600 megahertz of instantaneous bandwidth per channel. So there's a fair amount of bandwidth here that we can deal with. And then tying that in with an AI/ML accelerator. In our particular case, we're using the Google Coral TPU, their tensor processing unit, and we're focusing largely on TensorFlow, but there's nothing about the system that would preclude us from using PyTorch or Onyx or any of the other major AI/ML frameworks. We have a couple of different possibilities here, and we're actually investigating those in this fiscal year, taking the programmable logic and potentially implementing the DPU, which is the Xilinx equivalent of a tensor processing unit, in programmable logic, implement the DPU in PL, as well as being able to take certain versions of the actual AI/ML framework and convert them into VHDL and run them inside of the programmable logic as well. We've had very good luck so far with a model called TVM. It's from the folks at Apache. It does have a mechanism for being able to convert trained AI/ML models into programmable logic. So we're experimenting with that right now and getting reasonably good results out of that so far. Of course, then we tie in our open source framework. It is Linux based, of course. We are using Docker in this implementation, whether it's Docker, LXD, LXC, one of the other frameworks, OpenShift, what have you. Really doesn't matter to us at this point, but Docker is the one that most people think of when they think of containerization. And of course, Kubernetes as the container management system. Kubernetes itself, obviously, is relatively heavyweight. So we're actually using a lightweight version of Kubernetes called K3S. And again, we'll show a demonstration of that coming up. Here is our minimum viable product. This was the first generation board that we've got put together. This is the Barracuda board. It is using the generation 1 RF sock. That does limit us to no more than 4 gigasamples per second. The new 3rd gen stuff goes quite a bit faster than that. We do have on this board, we have the Google Coral TPU here. This is actually interfaced via PCIe, so this is a PCI Express interface rather than the typical USB interface. To give you some relative size, this is a standard RJ45 jack here, and we see it referenced to this quarter size, so you can kind of get an idea for exactly how big this particular part is. We do have all the RF down here. We've got external clock inputs, things of that sort. So this board is working. We're currently debugging the RF section right now. We do have the RF receivers working. We're currently checking on the RF transmitter side at this point. With some very good successes so far, and we're looking forward to bringing this board completely online here in the next couple of weeks. Because of the global chip shortage, this particular part here, this is a system on module from a company called Trends. These things are very difficult to get a hold of. We do have one of them, but because of the limited availability of these particular parts, we have been using the ZC111, which is a development board from Xilinx, to supplement the software development process. We'll see some examples of this here in just a second, so we'll kind of skip over that particular picture. And we'll kind of summarize here. The current Samosa is in testing. We have the minimum viable product up and running at this point. We are using Xilinx Petalinux. We are switching over at this point to Yocto, doing a straight up Yocto build because of some of the vagaries associated with Petalinux from time to time. The kernel has been patched to support Preempt RT, which is the soft real-time support kernel inside of Linux. We're experimenting right now with some use of the Pink application framework. That's being used largely for testing some of the SDR functions. We do have QPSK transmit and receive applications running. Those are currently being used to test some of our signal stability at the moment. And we have a Docker container that is running our mod classify AI engine that is being used to then characterize signals that are being recorded. We do have also the tasking of containers via K3S, and we're currently working on the deployment and actual development and deployment of a GNU radio-based and SOAPy SDR framework for execution inside of the containers. So with that in mind, let me go ahead and switch over to the demo portion of this. I will bring up Windows Media Player so you can see that. In this first little portion, we actually have a signal that's we're basically just pulling everything in off the air up to our first order Nyquist band, which is a 2 gigahertz. When we run that, you'll see this particular, we see both a spectrum analyzer and a waterfall plot going on here. The thing that's happening right here, where this lit up quite brightly, that is actually T-Mobile's 5G radio service sitting out there. The things that are happening over here on the left-hand side, these are actually Wi-Fi beacons. Right here, just about 1.6 gigahertz is where Wi-Fi's alias, of course, Wi-Fi in the 2.4 gigahertz band, it aliases itself down to just above 1.6 gigahertz into the first order Nyquist band. But we see here kind of the static plot of the signal coming in with a typical waterfall sort of thing. Next, we're going to switch over to the mod classify demonstration. And in this, we're running a Docker container. And inside of this Docker container, we have our mod classify application. It takes advantage of an AI framework in order for us to be able to then classify signals that are being received from the receiver in IQ format and bringing them through to try and determine whether or not, if we can identify this particular signal. So we start off running here. Let me just see if I can speed this up a little bit. We've pulled down the image. Now we're going to run mod classify without the AI accelerator. So we're doing a Docker run. And of course, we're pulling information. In this particular case, our mod classify, our Google TPU is setting out on the USB interface. And we're using the ZC111 board, one of the development boards, while we're still debugging our existing platform. And we see that it's going along here. It's pulling in IQ data. It's trying to determine what kind of a signal it is. We have, in this particular case, we have some truth data. So we're able to actually compare it against the truth data to determine how accurate we are. This does take quite a while. You can see how fast it's going out of 128 different signals. So let's see if I can sped this up just a little bit. And when it finishes, we'll see that we had about a 64% accuracy rate. Now we're going to run the same thing, except we're going to turn on the accelerator, turn on the AI accelerator. So from 64% accuracy, throughput about 5 kilosamples per second. When we turn on the AI engine, you will see that it is quite a bit different. So we're loading the TPU model at this point, and this is all tensor processing, and there you go. That's how it's running with the tensor processing unit. So we see that, first of all, our accuracy goes up from 64% up to 71%, taking advantage of the tensor processing unit. And our throughput is about 40 times faster than we were getting without using the tensor processor. So adding the AI engine here, the hardware accelerator, actually does have a fairly significant impact for this particular application. And we suspect it's probably going to have a better impact in certain other application areas. The last demonstration, because I'm just about out of time here, we're going to be running K3S. So we're actually going to be running Kubernetes, and we're launching multiple applications via Kubernetes. Again, this is on the same platform. We're going to then go ahead and use kube control to launch these things. For those of you who are familiar with Kubernetes, you recognize all of these commands. But what we're trying to do is we're just trying to make sure that our pod is being launched correctly. It is. We are, in fact, running 3 applications within this pod. And we're taking a look at the output from these individual applications. So they're all basically hello world type applications. But it appears that in this particular case, we are in fact running correctly. We are using K3S, and all of that is functioning correctly. We do have that now working with our mod classify application. So we can then now dispatch signal analysis platforms across the AI engines using Kubernetes type interfaces. So with that, I'll go ahead and turn it over to any questions and finish up because I've got just a couple of minutes left.
Yep, time for just a few questions. So I see one already. First one is, do you plan on using learning on target?
There is a model that is out there now that we've been talking to some of our folks about called MLOps. And whereas we have a DevSecOps kind of model to try and try to run on the platform itself, similar sort of thing is starting to happen in the MLOps world. Where there is the potential for being able to adjust models dynamically at runtime at the edge. We are still a ground demonstration at this point, so I don't have a good plan for that yet. But that is certainly one of the things that's on our list, to be able to do some actual learning on orbit, or at least modification of existing trained models on orbit.
Yep. Okay. Next question. You mentioned an open source framework. Do you have a link to that?
I do not at the moment, but if you want to reach out to me, I'll be happy to provide you that. We have some stuff out in GitHub, and I'll be happy to give you a pointer to that. I don't happen to have the link on hand.
Okay. Give another minute for any other questions.
Okay, it doesn't look like everybody's stupefied at this point. So.
Yep. All right. Thank you very much, Michael.
Thank you very much.